In this video, we are going to solve Cambridge International A's A-Level 9702 Paper 4 Variant 2, October November 2025. And it is, okay, I will try to go through the paper step by step, explaining each part in a way that very easy to follow, even for a weak student over there. And let's start with question one. Before starting towards the solution, I will say kindly subscribe the channel, like the video, share the video, and also comment if you have any question related to the topics and solution of these papers over there. Okay, let's move to question number one over here. Here he is saying that the Earth may be considered as a uniform square of radius 6.37 multiplied 10 to the power 6 meters. Consider Cambridge. Okay, Cambridge is at a point on the Earth's surface, has a latitude 52.2 degree north to the equator as shown over there. This is Cambridge and it is at latitude of the North Pole 52 degree with the equator over there. As the Earth spins on its axis, Cambridge moves in a circle that is parallel to Earth's equator but with the smallest radius. So show that the radius of the circle around which the Cambridge moves is 3.90 multiplied 10 to the power 6 meter over there. So he is basically asking to show that the radius is having this value over there. All right. I will say that as we know that the Earth radius which he has given to us is 6.37 10 to the power 6 meter. Radius is 6.37 multiplied 10 raised to power 6 meters, and latitude is which he has given us, that was 52.2 degree with the north of equator over there. North of equator, okay. 52 degree, theta is equal to 52 degree, 52.2 degree with equator over there, north of equator, north of equator over there. If I talk about little it, that he is saying that it is at latitude. If you just observe the word latitude over here, so latitude is measured from the equator. So at the equator, you are at distance r from the earth axis over there. What I will say, from the earth axis, you are at distance r over there. And as you go to north, your distance from the earth's axis gets smaller over there. And the distance from the earth's uh, axis will be taken as r cos latitude. So I will say r cos latitude. I am using r cos theta over there. So I will say that the radius r, this is capital R over there, which I am taking. So this is R is the radius of the circle, which I want to calculate over there, cos 52.2 degree. So R is 6.37 multiplied 10 raised to power 6 with cos 52.2 degree. So you will get all of this value by giving it to the calculator. You will get the answer 3.90 multiplied 10 raised to power 6 meters over there. All right, what he is saying next. Calculate the speed at which Cambridge moves around the circle over there. So we remember that the speed formula for Cambridge around the circle will be V will equal to circumference like 2 pi r over time for one rotation over there. So from here, I will say that as we know, circumference is 2 pi r and time is 24 hours over there, which will give you the whole value. So I am taking here 2 pi and I will have the radius will have the value that was taken according to it, 3.90 multiplied 10 raised to power 6. And for 24 hours, if you convert your time, 24 multiplied 3600 seconds, then definitely you will get your exact value, which you will get after getting your answer in 283.3 meter per second over there. So I have just placed the values over there. 2 pi r, just give all of these values to the calculator and get your final answer over here. After that, he is saying a student of mass 58.6 kg stands on horizontal ground in Cambridge. Determine the magnitude of the resultant force that acts to cause the circular motion of the student over there. So according to formula, if we know that we have two formulas, F is equal to mr omega square, or we can say we have the formula mv square over r. So mass is already given, speed is given, and radius you have. Just place all of those values to get over there. So I will say go for it. While like mass is 58.6, 8.6, and the speed which you have calculated 283.3, 283.3 whole square over radius should be taken as 3.9 multiply 10 raised to power 6 like the radius of Cambridge over there, and you will get your resultant force value as 1.206, and which you can say 1.21 Newton is the force for it. Here he is saying on the figure, draw arrow to show the direction of resultant force that acts on student. So direction of resultant force is centripetal force causing the circular motion. It acts towards the center of circle that Cambridge moves around towards the Earth's axis. So draw the arrow horizontally towards the axis, not towards the Earth's center over there. So we will have to say that it should be drawn. This is the Cambridge point. So I will say the circular motion is shown. It is directed towards the center over there, not towards the Earth center. Remember that this is the Earth surface being taken. So I will say draw always an arrow horizontally towards Earth's axis, and I will say that it will be horizontally towards it. Okay, what he is saying next, let's check over there. Here he is saying draw the labeled arrow from the student to show the direction of forces that act on student to cause the resultant force in B part 2. So from here I will say two forces causes the centripetal force, which I will say weight, that is W is equal to mg towards the earth center, and normal contact force from the ground slightly tilted from the vertical because earth is curved, so the horizontal component provides the centripetal force, and draw W downwards. So like weight is acting downward like this, yeah, or you can say like this, and reaction is slight angle over there, like little bit. I'm not taking exactly. Wait a second over here. I am saying that weight, if you are taking your weight towards inside, don't take your normal exactly in opposite way. Take it little bit showing a slight angle in this format over there. And so their vector sum has a horizontal component towards the Earth's axis over there. Okay, your weight is like this, and if you take both of them, your resultant should be taken like this, which can be taken in this format along the axis parallel direction over there. Here he is saying state Newton's law of gravitation So I will say according to the law statement over there, we can simply say that the gravitational or the force of attraction, the gravitational force of attraction is attraction between two masses is directly proportional to product of their masses and inversely proportional to the square of distance between their centers. And we can also say that F is equal to G m1 m2 over R square, where G is a gravitational constant over there. One of the basic assumptions of kinetic theory of gases is that there is no forces exerted between the molecules of the gases except during collision. State other two basic assumptions of kinetic theory of gases over there. So I can say the molecules of gases are in continuous random motion. Molecules of gases are in random motion. In random motion over there. And I can also add that the collisions with the walls of the container, the collision of gas molecules with the walls of container is perfectly elastic. Is perfectly elastic over there. Okay, these are the two assumptions which he was expecting from us. Hydrogen gas consists of molecules that each has a mass of 3.3734 10 is to a minus 27 kg. Hydrogen may be considered as an ideal gas. Okay, a spherical balloon of this mole of hydrogen gas at temperature of 282 Kelvin. At this temperature, the volume of gas in balloon is being taken this meter cube. Determine the pressure of the gas over there. So I will use simple gas equation formula over here. PV is equal to nRT. P is pressure, V is volume, N is number of moles, and R is general gas constant, which is having the value 8.31 with the unit joule per Kelvin per mole over there. So I need the pressure to calculate over there. Pressure of the gas, make pressure as a subject, nRT over V over there. N is number of moles, that is 0.016. 0.016 multiply R is general gas constant 8.31 multiply temperature is 282 over volume, that is 1.87 multiply 10 raised to power minus 4, everything in SI base units. So not to worry, just go for it 2 and give this all to calculator and you will get the value 2.0101 multiply 10 raised to power 5, or you can say it is approximately equal to 200,500 pascals over there. After that, he is saying estimate the average separation of hydrogen molecule in the gas over there. So if I go for average separation, then I can say that I will have to take volume per molecule. I will have to go for that. So volume per molecule, volume per molecule. I will get volume per molecule as I have the volume 1.87 10 is power minus 5, 1 point. So per molecule, okay. So I will have to go for getting the per molecule, like number of particles should be equal to number of moles multiply Avogadro's number. So I am saying here that volume over total number of particles can be calculated as 1.87 multiplied 10 raised to power 1.10 minus 4 minus 4 divided by number of particles from number of moles to be multiplied by Avogadro's number. So 0.016 multiply Avogadro's number have the value 6.022 10 raised to power 23. And if I get this to be given to the whole value over there. So volume per molecule will be 1.94 multiplied 10 raised to the minus 26 per meter cube. And if you want to get only one side separation, if we imagine that each molecule at the center of a small cube of side D, then D cube is the volume per molecule. And if I am saying it is D cube, definitely I will have to go for cube root over there. And if I get the cube root of this value, so your separation will get its value as 2.7 multiplied 10 raised to the minus 9 meter as the separation over there. Use your answer in C2 to calculate the average gravitational force between the adjacent molecules in hydrogen gas over there. So for this one, I will say I will have to use a law of gravitation formula G m1 m2 over d square like that. So for this one, I will say that I will have to use the mass of hydrogen particle which he has given as 3.34 10 is for minus 27 and gravitational constant value to be implemented over there 6.67 multiplied 10 raised to the minus 11. After that mass I am taking because it is taking in the form of product because m1 m2 both are same over there, so I will take its square 3.34 multiplied 10 raised to power minus 27 square divided by d is the separation which I have calculated right now 2.7 multiplied 10 raised to power minus 9 whole square. Give this whole value to the calculator over there and you will get your answer as 1.02 multiplied 10 raised to power minus 46 Newton over there. Now he is saying by considering the weight of a molecule suggests that with a reason whether your answer in D part 1 is consistent with assumption of kinetic theory of gases that there are no forces exerted between molecules. So if I go towards the weight over there, like as W is equal to mg over there, if I go for it, then I will say that I will have to use 3.34 multiplied 10 raised to a minus 27 into 9.81. If I go for it, I will say it is giving answer 3.28 multiplied 10 raised to a minus 26 Newton like that. So I will say gravitational force between the molecules is showing its value as 10 raised to a minus 46 Newton over there. So I will say which is much smaller than the weight. So gravitational force is negligible as compared to other forces. What I am saying, that the gravitational force is very, very much negligible as compared to other forces, and like collision. So it's consistent. It is consistent with kinetic energy assumption that there are no forces between molecules except during collision is fine for it. He is moving towards the question number 3 here, where he is saying state what is meant by two objects being in thermal equilibrium. So I will say, according to thermal equilibrium, I will say two objects are in thermal equilibrium when they are at same temperature. They are at same when they are at same temperature. So there is no net flow. There is no net flow. So there is no net flow of thermal energy between them. Of thermal energy between them. Then they will be in thermal equilibrium over there. After that, he is saying that figure 3.1 shows the type of a thermometer called constant volume gas thermometer over there. Okay, delta H is shown, liquid and gas is given. Okay, the thermometer is used to determine the thermodynamic temperature T of the gas bulb. Okay, and this the glass bulb is immersed in the environment for which the temperature to be measured, the height of the movable glass in tube then adjusted, and the level of liquid on the left hand side aligns with the reference of X marked on a fixed glass tube, the reference line Y marked on the side of movable glass tube, and Y is higher than X over there. Okay, the difference between the height is delta H at X and Y, then is measured using the scale. The thermodynamic temperature T of the gas is directly proportional to pressure of the gas, and this pressure is directly proportional to height. Okay, what he is asking over there? He is asking that the value of delta H can be used to calculate the pressure of the gas over there. All right. In order to do this, the gravitational field strength is used along the property of the liquid. State the property of the liquid that is used to calculate the pressure over there. So for pressure, I will say the property will be density. Density, because pressure is equal to rho g delta H, which means hydrostatic pressure over there. Okay, delta H can be taken as small. Hydrostatic pressure over there. Okay. After that, he is saying that before the measurement of delta H can be made, the glass bulb needs to reach the thermal equilibrium with the environment for which the temperature is to be measured. State two disadvantages of using constant volume gas thermometer to measure the temperature over there. So, two disadvantages. Okay. So for this one, I will say, okay, it is bulky and slow to reach equilibrium, slow to reach equilibrium, and I can say large thermal capacity is over there, and it is fragile, like I can say glass apparatus, like that it is fragile, like it is glass apparatus over there. Okay, let's move here. He is saying suggest one situation in which A constant volume of gas thermometer would be an appropriate type of thermometer chosen for measuring temperature. Okay. So for this one, I will say that when high accuracy is needed over a wide temperature range, a wide temperature range over there, then I will say calibrating other thermometers, calibrating brating other thermometers in the lab over there, in lab. Okay. Let's move to next. Level X aligns with 2.31 centimeter on the scale. At 0 degrees centigrade, Y aligns 8.69. At the temperature theta, Y labels 7.83. Scale determine the value of temperature over there. So I will say that temperature in degrees centigrade for 0 degree, temperature in 0 degree centigrade will equal to 0 degrees centigrade will equal to 273 Kelvin. And from here, I will say that at 0 degrees centigrade, Y is at 7.83, no, sorry, 8.69, okay, at 0 degrees centigrade, which he has told, and X at 2.31 centimeter. And that is fixed over there, by the way. So difference in height can be taken as delta H is equal to 8.69 minus 2.31, which will equal to 6.38 centimeter. And at theta, y is 7.83. So 7.83 minus 2.31 will give me the answer 5.52 centimeter over there at theta y. So at this is for temperature 0 degree centigrade, and it is for theta temperature, theta degree centigrade temperature over there. So for both of them, I will say that I will have to use that pressure is directly proportional to height over there, and thermodynamic temperature is directly proportional to pressure, which is proportional to height. So temperature over temperature at 0 degree centigrade will equal to delta H over delta H at 0 degree centigrade as original over there. So I will say, if I want to say that temperature, if I want to calculate, then definitely I will have to use both of those values by putting as their heights over there. Then it can be elaborated that T will equal to T 0 degree centigrade. I have used that 273 should be multiplied on this side, and the height which I want to calculate delta H for temperature 5.52 divided by 6.83, and if I get the temperature, you will get 236.2 Kelvin. And if you want to go for this to degree centigrade, just minus with 273, and you will get your theta temperature as minus 36.8 degree centigrade over there. All right, here he has shown over there that a cylinder contains a fixed mass of an ideal gas at pressure 2y and volume 6x. Pressure 2y and volume 6x. The gas undergoes a sequence of changes from its initial state A through state B, C, and D, and then finally back to the final initial state of A over there. Okay. X2x over there. as shows the variation of the time with internal energy of the gas. Okay, 0, 60, 20. All right, here he is saying state the first law of thermodynamics over there. Just simply keep in mind the formula that states that delta U internal energy is equal to heat provided plus work done by the system or on the system over there. What I am saying, delta U is change in internal energy. Change in internal energy, and Q is thermal energy. Q is thermal energy supplied to system over there. And in the end, I will say W is work done on the system. Work done on or by the system. Hmm. Okay, let's move to the next. What he is saying. Use figure 4.1 and 4.2 to determine the general expression for the internal energy delta U of the gas when it is if the pressure and volume is taken as V over there. So figure 4.2 and 4.1. If I take figure 4.2, okay, what I am saying, U is constant. U is as internal energy constant during the isothermal changes. Let's check that from the figure 4.1 as he is showing over there, AB is constant pressure over there, and BC is constant at volume over there. Then again, CD is constant at pressure P, and DA is constant at pressure volume V. And figure 4.2, U varies linearly with the time AB linearly, and U varies linearly with time in A and B, and CD is constant again, and in BC and DA also constant. So I will say actually for an ideal gas, U depends internal energy depends upon temperature over there, I can say. And I can also say that U is directly proportional to temperature. And if I use the formula PV is equal to nRT, let's go for its calculation little bit. I will say uh, what I am saying that PV is equal to nRT, and I can say T is directly proportional to PV because these two are constant, PV over there. And so U is directly proportional to, as I said, that temperature is directly proportional to internal energy. So U is directly proportional to pressure into volume over there. And from figure 4.2, okay, when he is saying that P is equal to 2Y, pressure is equal to I can say 20xy, okay, and V is 6x, U is again equal to UA, at B, P is equal to 2y, V is equal to 2x, so U smaller. So I will say U is equal to K dot PV, where K is a constant. So I am writing U is equal to K dot PV, where K is a constant over there. All right. An ideal gas at thermodynamic temperature T contains N molecules. Okay, use your answer in B1. Find the equation of state for an ideal gas to deduce an expression for U in terms of N and T and identify other symbols of use over there. So as we know that internal energy is equal to 3 by 2 nkt over there, and k is a Boltzmann constant over there. And then I can say U is equal to k dash PV, and PV is equal to nkt. So U is equal to 3 by 2 nkt over there, can be taken as the final relation over there. Okay, monoatomic gas, this is being taken, and for U as K dash V, PV is equal to nkt, and U we can get as 2 3 by 2 nkt, where K is a Boltzmann constant over there. Okay, here he is saying that determine the expression in terms of x and y for the work done of the gas during the change AB over there. So during the change AB, as I say, that P is equal to 2y, delta V is equal to being taken as for constant pressure. Okay, I can also determine little bit over here to for you that W will equal to minus P delta V. Okay, for constant pressure like that. Okay, and then WAB over there, then I will say that I will have to use this relation over there. Then the pressure is equal to 2y, then I can say it is going for minus into 2y into minus 4x is giving us 18xy over there. And for this one, change CD over there. If you observe your CD, then I will say P is equal to y, and delta V is equal to 6x minus 2x, which is equal to 4x there, and you are getting your relation as minus 4xy over there. Let's move to the last one. Here he is saying use your that the first law of thermodynamics to determine an expression in terms of x and y for the net thermal energy. Okay, for the net thermal energy Q supplied to the gas during one full cycle ABCDA. Explain your reasoning also. All right, for this one, I will say, as we know that for net thermal energy in one cycle, for a cycle delta U, change in internal energy will equal to zero, definitely. And first law states that zero is equal to Q plus work done as net over there. So from here, I can say Q is equal to minus work as net over there. So if I take according to the figure, if I take work along BC will equal to 0 because change in volume is 0 there, and DA, work done along DA, is also equal to 0. So net work will be 8xy minus 4xy, as we have already calculated here. Like it was 18, no, it was 8 by the way. Wait a second, it was 8xy. Okay, so I will say 8xy, and minus 4xy total is minus 12xy. No, minus 8. So the work net will equal to 8xy minus 4xy will equal to 4xy there. So Q is equal to minus 4xy. Q is equal to minus 4xy there. And here I can say negative means net thermal energy is released by the gas. So it will equal to minus 4xy over there. All right. Here he is saying that the steel ball on the end of oscillating mass spring is shown. X is the distance over there. The displacement of the center of the ball from its equilibrium position is x. Okay, this is the displacement. and acceleration is shown with -1 and 1 over there. Explain how figure 5.2 shows the oscillation of the ball or simple harmonic motion. So I will say how graph shows simple harmonic motion. I will simply say that in simple harmonic motion over there, what is happening? A is directly proportional to minus x. And so AX graph, as he has drawn over there, AX graph is straight line through origin, is straight line, through origin, through origin. Uh, so I will say with negative slope, with negative slope there, and this negative slope shows straight line with negative gradient is showing the um, simple harmonic motion. So fig 5.2 shows 5.2 shows a straight line with negative gradient, straight line with negative gradient, which is responsible for simple harmonic motion there. Determine the time period T for the oscillations over there. So if I go for its gradient over there, then I will say that it is showing its value at x is equal in centimeter. And if I take our gradient over there, x as 0.04, let's suppose it is, and I am getting from the figure, the gradient will be approximately like -20. And if I go for its getting its value as omega, and then I am arranging it for time period, then I will say that omega can be calculated as t is equal to 2 pi over omega. So from figure 5.2, I will say, as we know that the gradient is a is equal to minus omega square x. If I get the gradient, then gradient will equal to minus omega square. Let's suppose I am getting when x equal to zero point 0. Let's suppose I take this value here like this, then it is like this. Okay, I'm getting this value like 0.04 to get my value here, and getting my value here as 0.5 centimeter. 0.5 centimeter, it means in meters. If I go for it, I will say it should go for 0. X is 0.04, then my acceleration will be its value will be minus 0.80 meter per second square. So gradient will be 20, gradient will equal to 20 per second square. So it will equal to minus 20 per second square is going for omega square, taking the square root. So omega is equal to 4.472 and t is equal to 2 pi over omega. So 2 into 3.14 divided by 4.472, and we will get the answer over there at 1.405 seconds over there. For the next one, he is saying at time t is equal to 0, when displacement of the ball has its maximum value, the ball is immersed in a trough containing thick oil, that the ball is just below the surface of the oil over there. This results in the subsequent motion of the ball being heavily damped. What is meant by damping over there? Okay, so damping is when an oscillating system when an oscillating system when an oscillating system loses energy to surroundings loses energy to surroundings causing amplitude to amplitude to decrease over time is called damping over there. Here he is saying on figure 5.3, sketch a possible variation of displacement x of the ball with time t. T is 0 and 2t are shown over there. So t is 0, maximum displacement, amplitude decreases quickly without oscillating much, over damped. So curve returns slowly to 0 without crossing to the negative side much. So I will say that I will have to T0 at maximum displacement. Let's suppose I am taking 1.5 as maximum displacement. Amplitude decreases quickly without oscillating much, over damped over there. So I will say it is going to complete its, wait a second. I am saying that its amplitude is maximum. Now I am taking it like this. And to reach like this, then again going to down, taking it up and reaching like, wait a second, reaching like down and reaching like this. Okay, this is the phenomenons, and curve returns slowly to 0 without crossing to negative side much over there. Okay, so it is showing that a decrease in amplitude should be shown over there. I have taken less negative, then less positive, then less negative, then less positive to sketch up to 2 time periods over there. Let's move to the next. What he is saying over there, define an electric field at a point over there. So electric field at a point is the force per unit positive charge. Force per unit positive charge. Per unit positive charge placed at that point. Placed at that point. After that, he is saying on the figure 6.1, draw the electric field lines which represent the electric field outside the sphere due to the charge on the sphere over there. And it is a positive charge, as he has shown, plus 83 picocoulomb over there. Picocoulomb. Okay. So positive charge. So positive charge is this, and it should show relatively outward over there to show the electric field around it. Calculate the electric potential at the surface of the sphere over there, and we know that the capacitance C is equal to Q over V, and we want to calculate V over there. So we will say V is equal to Q over C, and Q was having the value 83 picocoulomb. So 83 multiplied 10 raised to the minus 12 divided by the value of capacitance is 69 picofarad. So I am taking 69 multiplied pico is again minus 12. So both of these are cancelled. 83 divided by 69 will give us 1.203 volt over there. Determine the radius of the sphere over there. So for this one, I will say that I will have to relate my radius with the capacitance man formula, which we know that the capacitance is 4 pi epsilon naught r. To make the radius of that sphere, I will make it as a subject over there. Then r will equal to C over 4 pi epsilon naught. C is the capacitance, which is being taken as 69 picofarad, 10 raised to power minus 12, divided by 4 pi, and epsilon naught is just like a permittivity of free space, which has the value as 8.85 multiplied 10 raised to a minus 12. 8.85 multiply 10 raised to power minus 12 over there, or you can also take its value like 9 multiplied times power 9 over there. 9 in case of Coulomb's constant, you can also take over there. Okay. 4 pi 8.85 times power minus 12 is permittivity of free space. If I give all of these values to the calculator, then I will get my whole value 0.62 meters over there. After that, he is saying calculate the electric field strength of the surface, give the unit of give your unit into your answer over there. So if we know that E is equal to Q over 4 pi epsilon naught R square, and because E is equal to V over R, from here we know that it is as a potential gradient over there, V over R, and I have the value of V now, that is 1.203. Okay, so I will get 1.203, and the radius which I have calculated here is 0.62. Wait a second, over 0.62. So from here, if you get your solution value, then it is 1.94, and the unit will be volt per meter over there. Or you can also write it over there as nm minus 1, nc minus 1, n Newton per coulomb, like that, nc minus 1 over there. After that, what he is asking over there, that the sphere is discharged connecting to the earth 0 volt through a resistor of resistance 120 mega ohm. Calculate the time taken for the charge to fall to 26 pico coulomb over there. So we know that it should be taken as Q over Q naught formation over there, and we should go for calculation of the value T over there. So for this one, I will say that T is equal to RC, but before that, I will have to use the quotient value Q over Q naught over there should be being taken in the form of complete logarithm. So discharging of capacitance, I am using the relation. Just look at here. Q is equal to Q naught e power minus T over RC. And from here, I will say R is given as 120 mega ohm. R is 120 multiplied 10 raised to power 6 ohm. This is my resistance value. And capacitance is being taken from the original value, that was 69 picofarad. So 69 multiplied 10 raised to a minus 12 farad over there. This is the capacitance, and RC, if I multiply both of them, then RC, which I can get over there after multiplication of both of them, will equal to 8.28 multiplied 10 raised to a minus 3 seconds over there. And if I go for Q over Q naught to get over there, so I will say Q over Q naught will give me the value of 26 over 83. Pico is cancelled from both of them, and I will get my value as 0.3133. And as a quotient value, so now I am using this e power minus TRC, and then I will get my whole value Q over Q naught and e power minus T over RC will equal to 0.3133. If I applied ln on both sides, ln into 0.3133 is equal to ln, making it 1, and minus sign is going to be taking it with this value, and T over RC, and By getting this value, I will say that it is 1.160, and from logarithm I'm getting negative value, which is also being ln e as 1, and minus t over rc. This minus is cancelled with this minus. After that, I will say now I will have to go for t to ln e is already made that it is 1. So RC is being going to be multiplied 2 over there. So it's T is equal to RC, which I have calculated there, is giving its value 8.85 multiply 10 raised to power minus 3. So 8.28 multiply 10 raised to power minus 3 is going to be multiplied with this value 1.160, multiply 1.160, and I am getting my value as 9.60 multiply 10 raised to power minus 3. So 9.60 multiply 10 raised to power minus 3 is the time in seconds over there. Okay, here it is, question number 7. When alternating voltage V varies with time t according to this equation, where V is in volts and t is in seconds. For an alternating voltage, show that the period is 0.50 seconds over there. So if I look this relation, we know that V is equal to V naught cos omega t. So omega is being shown as t is equal to t. 40 pi is being shown as omega. So omega is equal to 40 pi. Omega is equal to 2 pi f is equal to 40. And from here, if I want to take omega is equal to 2 pi over t, omega as 2 pi over t can also be written equal to, as frequency is reciprocal of time period over there. So reciprocal this, so t is there, and 2 pi over 40 is equal to t. If you divide it over there, then 40 pi, it is 40 pi. 40 pi, 40 pi, 40 pi. So pi and pi is cancelled, and you are getting 1 over 20, which will equal to 0.050 seconds over there. So this time period is shown for it. After that, determine the root mean square value of voltage. You remember that root mean square value VRMS is calculated by V naught over under root 2, and V naught, which you have from your formula, is being given as 18 over there. So 18 over under root 2. If you do its simplification over there, you will get 12.7 volt. After that, he is saying that sketch the variation of V from T0 to 100 milliseconds. So it is a cosine wave, so amplitude will be 18 volt, which I can show from here. I can show from, this is 18 volt, okay? 10, 12, 14, 16, 18. So it is 18, and it is going for 100. So for 50, I will have to complete the cycles over there like this and this. Again, I'm showing with 18 also. Then I am showing it here and going to take it here. Then I am showing it here. Then I am showing it here. Then again showing here. Then again showing here. So this is the way how to go for drawing the graph over there by showing from 0 to 100 milliseconds over there. Let's move next. What he is saying that the alternating voltage is rectified to produce an output voltage across load resistor R as shown. Okay, rectification circuit, voltage and resistance output voltage over there. Here he is saying that which shows the variation of this. Okay, means amplitude is enlarged over there. from 20 to 28. Okay, it is shown the power. It is shown the power versus time of rectified output over there. Okay, state three conclusions which we can draw from the conclusion of qualitative or quantitative use your space for any working over there. So I will say uh, power is always positive. So we can say here that power is always positive during rectification. Power is always positive. It will not be shown with the negative axis over there at all, like it is rectification during rectification over there. And at number two, I will say power peaks after every 0.025 seconds, peaks every 0.025 seconds, like half period of input voltage like that. And average power is always less than uh, than peak power due to ripples, due to a ripple over there. All right, in figure 8.1 shows three lowest frequencies lines of part of emission spectrum of hydrogen that relates the electron transition of the ground state N1, 3.09, 2.92, and 2.47 not to scale. The number of the frequencies 10 raised to 15 hertz has to, okay, use the photon model electromagnetic radiation to explain how the existence of spectral lines in the emission spectrum provides the evidence for discrete electron energy levels in the hydrogen atom over there. All right. So for this one, I will say that we should go for it like photons emitted, like he is asking basically spectral lines evidence for discrete level. So I will say photons emitted, photons emitted, photons emitted when electrons drop from, when electrons drop from higher to lower energy levels, higher to lower energy levels, so specific frequency F means specific frequency F means that um, that specific energy difference, specific energy difference, like delta E is equal to HF, and lines in spectrum, in spectrum lines in spectrum are only containing delta E, a load, are only containing delta E allowed, and discrete energy levels are there. Discrete energy levels are there. So now he is moving the energy of the ground state in the hydrogen atom is 13.6 electron volt with negative sign. Calculate the energy in joules for the ground state over there. All right, for this one, we will say that N1 in the hydrogen 13.6 over there. So the difference between the both of these values like 13 and for N1 to N2 will be 10.2 electron volt like that. Okay, I go for it, no problem. Wait a second over there. First, we will have to go for energy 13.6 electron volt to joules over there. Joules energy. Okay. So I will say 13 point minus 13.6 electron volt multiply 1.6 multiply 10 is to a minus 19. So I will say I will get the answer 2.176 multiplied 10 raised to the minus 18. 2.176 multiplied 10 raised to the minus 18 joules over there. Show that the energy difference between N1 and N2 is 10.2 electron volt. Okay. If we will look towards the energy levels, if I go for E1 and E2 over there, so E1 will equal En as a general formula is equal to 13.6 over N square electron volt. If I go for first shell over there, 13.6 with negative sign over 1 square is equal electron volt. So it is minus 13.6 electron volt. After that, this is for first shell. For second shell, it will be minus 13.6 over 2 square making 4, giving you answer as minus 3.4 over there. And if you get the difference of both of them, then it is minus 3.4 with minus 13.6. So minus minus plus 13.6 is subtracting. So that is 12.2 electron volt is shown over there. After that, he is saying complete the table 8.1 to show the energy difference from the ground state and the energy differences to overlap of the levels up to N4 in the hydrogen atom. Use the space for any working over there. Okay, for E1, E2, I have already taken. If I go for E3, then I will say it is minus 13.6 and 3 square is 9. That is minus 1.511 electron volt, and E4 will be minus 13.6 over 4 square is 16. I will get the value minus 0.85, so electron volt over there. And the if I so I will say N2 is 10.2, which I have already calculated. So E2 was 10.2 electron volt, and 3 is having the value 10.2 was taken as a difference over there. And if I want to calculate for the third subshell with the first subshell over there, then that will be 12.1 electron volt. And if I go for first shell and fourth shell, then the difference will be this was for n is equal to 2. When n is equal to 3 from the subshell, then I will have the energy difference of 12.1 electron volt. When n is equal to 4, then it will be 12.75 electron volt over there. So let's go for all of these values over there which he is saying to go. N is 10.2, so I am using the other one values also over there. So that is 12.1, and for n equal to 4 is 12.75, and energy in electron volt is being taken 12.75 minus 13.6. I will get minus 0.85 by getting the difference of both of them. So after getting 12.1, I will get minus 1.51 and I will also get minus 3.40 and minus 13.6 over there. So we can say here, state what is meant by the mass defect of a nucleus. So mass defects, I can say the difference between the difference between mass of separated mass of separated nucleons nucleons like protons and neutrons over there, and mass of a nucleus, and mass of a nucleus over there. After that, he is saying that the nuclear fusion reaction from the formation of helium-4 and deuterium is represented by H1, like deuterium making helium over there. And the mass of deuterium is shown. Calculate the energy released in the formation of 0.1 mole of helium-4 over there. All right. So first of all, mass loss we will have to calculate over there. And if we will have to go for hydrogen masses over there to be taken, then I will say as mass on left hand side of the equation, if I am taking 2 hydrogen plus 2 hydrogen as a deuterium over there to make 4 helium over there as its nucleon particles over there, then I will say that mass on left hand side will be being taken as 2.013535 being multiplied by 2 over there. I will get 4.027106 unified atomic mass over there, and mass on right hand side is given by this value. If I subtract both of them, then I will get the mass loss or mass defect over there, and the value comes 0.025601 units over there. And according to Einstein's equation, E is equal to mc square. E is equal to mc square. Wait a second, it is showing a little bit hanging over there. So E is equal to delta mc square. So I can say that I will have to use this mass, which was being taken as 1.66 10 to the power minus 27, so that I can get it into the kg form over there. So delta m will be replaced by its value 0.2560. So when we will take the energy over there, then I will say by putting this value, I will get better 1 UC square to use 9.931. So delta E is going to 0.025601 is multiplying by 1 UC square, like 1 UC square. What I am saying over there? That is basically 3 multiplied 10 raised to power 8 whole square, and it is being multiplied by 1.66 multiplied 10 raised to power minus 27, and you will get this whole value to be taken as 931 31.5 mega electron volt. And if I am using this relation to be multiplied by this mass over there, then I will say that it is 23.85 mega electron volt per helium for nucleus. So if I am going towards 1 mole, so I will have to take Avogadro's number over there, which should be multiplied by this 6.02 multiplied 10 raised to power 23. So if I multiply this, then I will get my value in electron volt, and for getting it in joules over there, I will have to also be multiplied by 1.6 multiplied 10 raised to power minus 19 there. And after simplification of this complete whole value, I will say I will get the value 2.30 multiplied 10 raised to power 12 joules over there. Here in the part C, what he is asking over there, he is saying that the star of Sirius is the radius this and mass of nuclear fusion of the rate 1.9 times power 11 kilogram per second. Assume that the power of radiation emitted by the star is equal to power released by this process. Determine the value of luminosity of Sirius given the unit with your answer also over there. So for this one, I will say that as we know, luminosity is equal to mc square. So I will say mass is 1.19 multiplied 10 raised to power 9 multiply by c square 3 multiply 10 raised to power 8 whole square over there. And if you get the simplified form over there, then you will get 9.81 multiplied 10 raised to power 27. So 9.81 multiplied 10 raised to power 27 and unit will be watt over there. In the next part, he is asking, use your answer, determine the surface temperature of Sirius over there. So for this one, I will say that I will have to go for surface temperature. So temperature is being a relation T power 4 is equal to luminosity over 4 pi r square, where being taken with the Wien's displacement constant, little bit sigma constant over there. So if I go for this whole relation by taking the temperature whole power 1 by 4 also, so I will get my temperature only over here by putting all of these values. As I am saying, R is 4 pi into r square. So r is 1.1.19 multiplied 10 raised to power 9 with square, and Wien's displacement constant is having its value 5.76 multiplied 10 raised to power minus 8, and luminosity which you have calculated 9.81 multiplied 10 raised to power 27 with whole power 1 over 4, and you will get your temperature in Kelvin. That will be 9940, which is approximately equal to 9900 Kelvin over there. Okay, now he is saying explain how cosmologists use standard candles to estimate the distance of galaxy from the Earth. So standard candles have known luminosity. Standard candles have known luminosity L. So scientists measure the apparent brightness. So cosmologists measure the apparent brightness, measure the apparent brightness, measure the apparent brightness I at Earth, I at Earth over there, and then use the formula I is equal to L over 4 pi d square, where to find d over there. Okay, this is the whole method to go with the standard candles. Okay, so here he is saying state what is meant by an X-ray image. By contrast in an X-ray image over there. Okay. So it is the difference in brightness. It is the difference in brightness or darkness between different regions of image image due to different to different absorption by tissues. All right. Here he is showing that 2.1 centimeter material. This is going towards A. All right. Incident X-ray I naught. Detected X-ray 5.8 centimeter. Total muscle thickness. Okay. Material P has a linear attenuation coefficient of 0.35 centimeter. 0.53 show that the intensity is this. All right. So for this region, I will say that when he is giving this whole relation over there, I will say that first of all, given material with P thickness is 4 centimeter, which is given as 5.8 and 2.1. All right. So attenuation coefficient is for P is 0.35 centimeter for P, 0.35 and 5.8. So, and for region A over there. So it is a region A and it is region B over there. Okay. So for this one, we can say we will have to use simply, this is a 1 mark question over there. And I will say that we should use our, show that the intensity, is 0.13 nod and determine for the coefficient also. So I will say this is for 1 mark only. Okay. I will say that if I am taking here uh, I of B, intensity of B, I naught e power minus 6 mu for Q over there, 6 mu for Q over there, and e power minus 6 mu Q, then it is 0.2149 and IB is 0.213, 0.213 and 0.53 I naught he has already given over there. Just use 0.13 I naught over there. I'm just ignoring this answer, okay? I'm not going to waste too much time over here. Ignoring this part. Later on, I will explain also. After that, he is saying determine the linear attenuation mu for material over there. So from here, from earlier over there, if I go for it, I will say that 0.2466 dot e power 6 mu q over there is equal to 0.053 and e power it is minus 6 mu for q over there will equal to 0.2149 and take ln on both sides and you will get minus 6 mu q will equal to ln with 0.2149 over there, and by taking ln of this you will get minus 1.537. So I am saying that minus minus both are cancelled and dividing by this on that side you will get minus 0.256 per centimeter over there. Let's move to the next. Use the information in B1. Suggest why the X-ray emerging from the structure from an image has a poor contrast over there. Because The intensities emerging intensities emerging in region A and region A and region B over there are not very different, are not very different, like 0.053 I nod versus 0.13 I nod, 0.13 I nod. So contrast between region is low. Contrast between regions is low there. Okay, what he is saying for the last, explain how X-ray are used in computed tomography scanning to produce a three-dimensional image of an internal structure. All right, so I will say X-ray produced through X-rays produced through X-ray passed through the body. Wait, produced, no, passed through body. X-ray pass through body from many angles, and detectors measure transmitted intensity, transmitted intensity, transmitted intensity, and computer uses absorption and computer uses absorption data to reconstruct 3D image, reconstruct 3D image via via tomography over there. Okay. Okay, guys, it was the whole paper. Only one mark question, little bit skipped by me over here. That is related to question number 10, part B1 over there. Remaining all to all whole paper is done for you with complete explanation and details. Thank you so much for watching till here. See you in the next paper and next video. Stay blessed, stay tuned. If you want online tuitions, by using via me, kindly join on my channel. Description over there, link is provided in WhatsApp, link is provided, and you can easily communicate with me. Thank you so much.